Hello. Today I'm going to prove to you a very simple mathematical idea. Why the exterior angle of a triangle is equivalent to the two angles inside of the triangle that it does not touch, known as the remote interior angles. Now there's a very simple mathematical proof that goes with this, but it's predicated under two ideas. First, the Triangle Sum Theorem, that is how all of the interior angles of a triangle add up to 180 degrees. So that is, in my diagram, I have angle 1, 2, and 3. All three of them, under the Triangle Sum Theorem, add to 180 degrees. So I'm going to note that. Angle 1 plus angle 2 plus angle 3 equal 180 degrees. One very simple, well-known trait. Additionally, I am also aware that angles 3 and 4, well, those angles combine to make a straight line, also known as a set of angles known as a linear pair. And when two angles make a straight line, you have a linear pair. Those two angles themselves also add to 180 degrees. So in this case, angle 3 plus angle 4 add to 180 degrees. So I'm going to note that as well. Angle 3 plus angle 4 equal 180 degrees. Now, using a simple substitution idea, I have three angles equaling 180 degrees. I have two angles equaling 180 degrees. They both equal the same thing, so I can make these three angles equal those two angles. So angle 1 plus angle 2 plus angle 3 will equal angle 3 plus angle 4. Doing a little simplifying, I note there's an angle 3 on each side of my equation. Those cancel. I see that angle 1 plus angle 2, my two remote interior angles of my triangle, they equal angle 4, the exterior angle of my triangle. A very simple, straightforward mathematical proof why the exterior angle of a triangle, its measure, is equal to that of the sum of the two angles it doesn't touch, the remote interior angles of the triangle. However, I don't know about you, and while math is quite awesome, I am a visual person. So here's something I also did to further demonstrate this point. I took the triangle itself, and I just made a replica, and I decided to color code my angles as such. No big deal. However, I did a little extra, and I decided to take this triangle, rotate it, translate it a variety of times. So much so, in fact, that I came up with the following tessellation. It is this triangle rotated and translated several times. A very nice diagram if I don't say so myself. If I overlap it, you can tell it is, in fact, the same triangle. So here's what I noted. I noted that throughout my tessellation, there are several examples of where I see a triangle and its exterior angle, and I noted that as such. There's one example of that same triangle, this one, with its exterior angle. What I did was I color-coded all the angles, as I did over here, as well as the exterior one. And as I remove the tessellation, I see that my exterior angle, angle 4, is both red and green in color. The two remote interior angles, angles 1 and 2, are also green and red in color. A very nice, easy visual, further proving why the exterior angle of a triangle is equivalent to the two angles of a triangle it doesn't touch, the remote interior angles.